Okay, so here we go on alkynes. So we know an alkyne, what it looks like, is a carbon-carbon triple bond. So each of the carbons is sp hybridized, so they each have 2 leftover p orbitals on them. So if we draw the orbital picture of an acetylene, the simplest of all, we have the sp orbitals in the plane holding everything together from the hydrogen, the carbon to the carbon to the hydrogen, and then we have one p orbital in the plane of the iPad, and then we'll have another one 90 degrees to that going out in front of the iPad and going behind with the overlap there to make up the second pi bond. Okay. So we know how to name things. Pentane, it has 5 carbons, it's an alkane. If we have an alkene, it's a 1 pentene if it's on the end, 2 pentene if it's on the second carbon, so on and so forth. And if we go to a triple bond, they end in Y and E for the alkyne. So this would be 1 pentyne. 1 pentyne is a terminal alkyne where it is on the end of the chain, so it has 1 hydrogen off of it. 2 pentyne is an internal alkyne where it has alkyl groups off of each end of the triple bond. So they have one difference in reactivity of these two that we'll get to in a little bit. So to name things, 2, 3, 4, 5. This is a 1 pentyne or pent-1-ine, and off of it we have a 3, 4 dimethyl 1 pentyne. Okay, the next one is 1, 2, 3, 4, 5, 6 carbons, so it is a 2 hexyne. The next one is labeled wrong. It needs to be a 3,3-dimethyl 1 hexyne. So we have to have the methyls on carbon 3, the alkyne on carbon 1, so on and so forth. And then the last one, 1 octyne, 4, 5, 6, 7, 8, has a 4 ethyl, 1, 2, 3, a 3 propyl, and a 5 methyl. So that would be the last one there. Now, we all remember from the beginning of Org 1 where we talked about the hybridization and the pKa. An alkane is the weakest acid, pKa of 50. There's 2 things we can do to an alkane. We can burn it or we can brominate it. Okay, so we can put bromine on the most substituted carbon in a free radical bromination, or we can burn it and turn it into carbon dioxide and water. Ethylene or ethene, either one, has a pKa in the upper 30s to about 40, so it's a little more acidic, but still you have 4 different hydrogens on that alkene. How are you going to get them to react differently? You can't. There's not much we can do with an alkene. An alkyne has a pKa of 25, and we can selectively take off 1 hydrogen over the other to make it nucleophilic. So if we have a strong base, we can remove the hydrogen off of acetylene to make the acetylide ion, and then we can do something with the acetylide ion to displace something with a leaving group on it. Okay, so from acetylene, we need to make sure we always add a stronger base than the conjugate base of the acetylene to make sure we pull off the hydrogen and force the equilibrium to go towards the products of making the acetylide ion. So NH2 minus or CH3 minus are the best choices for removing that hydrogen to make sure all of it is removed to form the acetylide ion. If we just use hydroxide, we know the pKa for water is 16, so between our 2 acids in the reaction, the water is a stronger acid. So if we just add hydroxide, nothing's going to happen because the equilibrium favors the starting material, because in equilibrium, you always go to the weaker acid and weaker base. So previously we've shown the preparation of alkynes, where we can do an E2 elimination and form the alkene. So to form an alkyne, what we need to do is do 2 eliminations. So we need to have 2 leaving groups on it, either on the same carbon or adjacent carbons, to do the 2 E2 eliminations to form the acetylene. Okay, so the basic mechanism is shown below, where NH2 minus grabs a hydrogen, kicks off a bromine, then a second NH2 minus grabs a second hydrogen, kicks off a bromine, and we end up with the acetylide. Okay, now in this, if we have form a terminal triple bond, which we always will form a terminal triple bond, it'll walk its way down the chain, that's for later, we'll get to that. But we form the acetylene, and then NH2 minus can remove that extra hydrogen to form the acetylide. The acetylide with ammonia can't go back, so once we form the acetylide, we're done, and then we work it up with a dilute acid and protonate that to make the acetylene, the terminal acetylene. So this is a very good way to form a terminal acetylene. Now, acetylenes, or alkynes, we can reduce with 3 different ways. With hydrogen and palladium, we completely reduce the alkyne all the way to the alkane, because there's nothing to stop the reduction. With barium sulfate and quinoline added, we end up getting the cis alkene. And with sodium and ammonia, we go through a radical process and form the trans alkene. And those are the ways we can reduce a triple bond. So remember back in the chapter where we did the addition of HBr to a double bond, the pi bond attacked the hydrogen, it went to the least substituted carbon, and then the bromide added to the more substituted carbon. With a triple bond, we see here we have 2 pi bonds, so it's just going to do this mechanism twice. So on the next page, we have the mechanism where the pi bond goes and grabs the hydrogen to form the vinyl cation, shown here. The bromide adds to that vinyl cation to form the vinyl bromide, and then the double bond goes and attacks the hydrogen, kicks out the bromine, forming a new cation here, and the bromide adds to that to give us the 2,2-dibromo alkane. Okay. Now, in this, the mechanism will always be the same. We'll always get the bromines on the more substituted carbon of the triple bond. If there isn't a difference in substitution across the triple bond, then you get a big ugly mess. So on the test, there would always be a difference in substitution of the triple bond. It would be a terminal one, so that we had some control over what we wanted to form to make sure it did what we want. Okay, so there won't be a lot of choices in that. We can hydrate an alkene like we did in the last section, where with borane we added the boron to the less substituted carbon, the hydrogen to the more, and then oxidized off the borane to give us the alcohol. The same sort of thing happens here, where in the first step we can get to, if we simplify it a little bit, the borane and the hydrogen across the double bond. We can oxidize the borane off to the vinyl alcohol, enol, and then that can keto-enol tautomerize, which we will draw in a minute, to the aldehyde, because the carbonyl is more stable than the enol. Okay, and the enol is an enol because it has the carbon-carbon double bond, the ene, and the alcohol, they all attach together in it. Okay, and we'll draw that in just a second. But in it, we always put the oxygen with the borane on the less substituted carbon of the pi bonds. Here we have 2 pi bonds in the alkyne, so we get 2 bonds to oxygen in our andine carbonyl. So if we have the mercury acetate in water, we showed before, we've drawn the mechanism many times where the pi bond grabs the mercury, you kick out an acetate, water adds to that more substituted side, you take off the extra hydrogen. We've drawn that mechanism many times, and then you reduce off the mercury to form the more substituted alcohol. So in this one, we're going to get pi bond, well, let's draw a mechanism for it. The pi bond is going to add the mercury, so you're going to end up with the mercury on the less substituted, with the oxygen on the more, and we reduce off the mercury to get the vinyl, the enol, and then from the enol we can tautomerize it to the ketone form. But just like with the double bond, the OH ends up on the more substituted carbon of the pi bond containing molecule. Doesn't matter if it's a double bond or a triple bond, the oxygen ends up on the more substituted. With a triple bond, we're breaking 2 pi bonds, so we have to form 2 bonds to oxygen in our product. So with a triple bond, we either get ketones or aldehydes out of the reaction, not alcohols. So how do we draw this mechanism going from the ketone form to the enol form? If we're in acid, we have to protonate the carbonyl first. We can draw a resonance structure, moving the positive charge to the carbon, and then we can have water remove the extra hydrogen to form the enol. Okay, and we can do this middle part either in 1 step or 2, where we can combine removing the hydrogen to form the double bond. Here, we'll draw it on the next page. So both get to the enol. If we're in base, we need to show our hydrogen. So our hydroxide base goes and grabs the hydrogen to form the negative charge. We can draw a resonance structure, sending the electrons up to the oxygen to make the enolate, and then that can go grab a hydrogen off of water to form the enol. Okay, so we can do it the long way, or we can draw it the short way, just like in acid. Protonating the carbonyl happens first every time. There's no change in that because we're in acid. But from there, we can have water come in and grab the hydrogen, form the double bond, and kick out the bond to the oxygen to make the enol all in 1 step, or we could draw it like we did in the last one, where we drew it in 2 steps. Either way is fine. In the acid catalyzed, but in the base catalyzed, we can have the hydroxide come grab the hydrogen, form the double bond, send the electrons up to the oxygen to make the enolate all in 1 step, and then that can go grab a hydrogen off of water, not acidic water, sorry, off of water to form our enol. So we can draw them either way. Either way is fine, either the long way or the short way, both the acid or base catalyzed. It's up to you how you want to draw it. Okay. Now the next thing we can do is we can brominate an alkyne, and remember with the double bond, we added the bromines anti to one another. So if we add one equivalent of bromine, we're going to only add one bromine on each end, and the major product is the anti-addition. And the mechanism for this is the pi bond grabs a bromine, you kick out a bromine, and we have the vinyl cation, and then the second Br minus adds to that to form the dibromo compound. If we have an excess of bromine, and so we add one equivalent, just like before, where we get to the vinyl dibromide, and then just like the mechanism with the double bond, because this is a double bond, we have to go through the bromonium ion, open it up to get the tetrabromo compound. So with an excess of Br2, it'll go all the way to the tetrabromo compound, and we can't stop it at the dibromo. And this mechanism is a really good mechanism to ask on tests. It's been seen a lot because you have to be careful what you do. In the first step, there is no bromonium ion formed in the formation of the vinyl dibromide because of the bond angle. We all know the bond angle of the bromonium ion formed from the double bond. That bond angle is 60 degrees. If we have a double bond still in there, we cannot form this with a 60-degree bond angle between the bromine and the two carbons. We can't form that. So in the mechanism, we have to be very careful that we only show the vinyl cation and then add bromide to that. And in the second step, the addition of the last two bromines, 3 and 4, we do form the bromonium ions. You have to be careful how you draw things in this. Keep going. In the alkene chapter, with ozone followed by dimethyl sulfide or zinc and water, we cleave the everything between the two carbons and form two carbonyls. With the reductive workup, dimethyl sulfide or zinc and water, we got an aldehyde and a ketone. Out of the hydrogen peroxide, the oxidative workup, we get the carboxylic acid with a double bond. With a triple bond, it doesn't matter because we have to cleave all 3 bonds between the 2 carbons, so we're going to end up forming a carbon with 3 bonds to oxygen, or a carboxylic acid out of the reaction with a triple bond. There is no ifs, ands, or buts about it. We get a carboxylic acid every time out of the triple bond because we're breaking 3 bonds to carbon. And in that, we're going to replace them with 3 bonds to oxygen. Okay. If we add an alkyne and potassium permanganate and heat, we get the same product because we completely cleave all 3 bonds between the 2 carbons. We get 3 bonds to oxygen. We get the carboxylic acids again. If we have KMNO4, water, and neutral conditions, we only break the pi bonds. So we're breaking 2 pi bonds, we're replacing it with 2 bonds to oxygen. We get the dicarbonyl compound. So the other thing we can do with the terminal triple bond is we can deprotonate the triple bond to form the acetylide. The acetylide can do an SN2 displacement on an sp3 hybridized bromine that's on a primary carbon. It can do an SN2, and we can lengthen the chain. So we went from 2 carbons in our acetylene to 5 carbons in our one pentine, excuse me. Then we can remove the extra hydrogen off of the other end to form the new acetylide and do another SN2, and we can add something to both ends of the triple bond. So this is pretty much all of the reactions that we can do with a triple bond, and They're all the same things we could do with the double bond, just one more, except for this page right here, we can remove the terminal hydrogen from a terminal triple bond. Okay, so this is the one thing that's different between a triple bond and a double bond. Now I'm going to make this video, post this one, and then we'll do the last part of this where we review a bunch of things from Org 1.